All right, in the next section of the course, we're going to be discussing waveguides. So, as kind of a review, let's think first of all of what we've discussed so far. So, basically, what we've been talking about is the propagation of electromagnetic waves through space, through empty space, and we've also talked about how those electromagnetic waves interact with boundaries. So, when an electromagnetic wave propagates out, and if we get far enough away from sources, they all look like point sources. So, we can consider that it's a point source or a point antenna that's actually generating the electromagnetic wave. And it then leaves that source, it does so as a spherical wave. It travels with equal velocity in all directions when it's in free space. Now, if we get far enough away, which means the distance away is much, much greater than the wavelength of the traveling wave, we get far enough away from the source, basically we can approximate the spherical electromagnetic waves as a uniform plane wave. And so what we mean by uniform is we mean across the plane that's perpendicular to the direction of travel, the electric and magnetic fields are constant, and we mean that its direction of travel is in a direction that is perpendicular to both the electric and magnetic fields, and that the electric and magnetic fields are perpendicular to each other, that the wave fronts are planes that can be defined with rectangular coordinates. So we can use an XYZ coordinate system to describe the propagation of the wave and the directions of the fields. Now, in a wide range of electromagnetic applications, basically we want to move um, electromagnetic waves, we want to move information or energy from one point to another, and typically this is quite doable by means of unguided electromagnetic waves that propagate in free space. And for example, things like your cell phone, and back in the days before cable, when we had broadcast television, broadcast radio, all of those applications, the electromagnetic waves basically propagate through space. They're picked up by antennas, by receiver antennas. However, in some applications, we want to transmit these waves or signals that by using waves that are guided by metallic or dielectric structures. Now, what that does is it minimizes radiation losses, and it also prevents unnecessary spreading out of the energy. So if we really need focused energy delivered from point A to point B, if we can transmit that using a structure so that we prevent um, that spherical spread of energy in space, then that can be really helpful as far as delivering energy or enough energy in the signal so that we can pick up information. So guided transmission of waves also facilitates the use of a single frequency band to transmit multiple signals simultaneously, because a lot of waveguides, most waveguides can be laid very close to one another without significant coupling between them. And electromagnetic waves are generally guided by confining them in two dimensions and allowing them to propagate freely in the third dimension. So as we discuss waveguides, we'll look at how this confinement is done, and we'll look at what happens to Maxwell's equations when you then impose these boundary conditions on the traveling waves. So first of all, we'll start with discussing a parallel plate waveguide. It's the simplest example. Basically uses two separate conductors, and the conductors are used to guide electromagnetic waves. All the methodologies that we used in the analysis, these are directly, or that we will use in this analysis, are directly applicable to other systems that use two separate conductors that are symmetrically arranged. So a coaxial line, two-wire line, a twisted pair, etc., which can support the propagation of transverse electromagnetic waves, or TEM waves. All right, so what are TEM waves? TEM waves are transverse electromagnetic waves, meaning that E and H are perpendicular to each other, and they're perpendicular to the direction of propagation. Now, uniform plane waves, which is what we've been discussing in the past, are transverse electromagnetic, but not all transverse electromagnetic waves are uniform. So what this means is there can and will be spatial variation of the E and H fields in the plane that is perpendicular to the direction of propagation. So that's the main difference that we're going to encounter as far as the wave itself in a waveguide is that we do find that if we go in the different directions, in the x and y directions, if propagation is in the z direction, we'll find variation of the values of the field. All right, so here's a picture of the parallel plate, a typical parallel plate waveguide. And there are a couple of assumptions that we'll make. One is the z direction is going to be the direction of propagation, and so we're going to assume that the parallel plate guide is infinitely long in the z direction. We're also going to assume that it's infinitely wide in the y direction. That's a good assumption as long as the width of the waveguide is significantly larger than the space between the plates. What we're actually doing there is, in a real system, the electromagnetic field will be fairly uniform between the plates until you get to the edges. And as you may remember from fields 1, anytime you have a sharp edge, that causes a field concentration at the edge or at the corner. And so that's referred to as field enhancement. And then it also causes the fields to fringe. It's called fringing fields, which is what happens when you have an abrupt boundary here between two plates and then free space. You get some fields that quote unquote leak out of the edges. So if we make the y direction very big compared to the spacing between the plates, we can minimize that effect and we can approach the ideal case where we would have infinite width. Also, we'll assume the material between the plates is a lossless dielectric. So, in addition to supporting TEM waves, a parallel plate waveguide also allows the propagation of more complicated electromagnetic waves. In this case, the magnetic or electric field in the wave can have a component actually in the direction of propagation. So the presence of electric and magnetic field components along the direction of the propagation requires that the field components vary with position along the planar phase fronts. Okay, in English, that means if you go in the x or the y direction, that you will see the value of the electric field change in those directions. So such waves are called either transverse electric or transverse magnetic. And basically what happens is, in solving the differential equation, you can get a number of different workable solutions. And we just refer to those as modes that can occur in the waveguide. So once again, here's a picture of our parallel plate waveguide. The simplest type consists of two perfectly conducting plates between which the electromagnetic waves can be guided. Once again, they have an infinite extent in the z direction. They have a finite width, but it's considered to be much greater than the plate separation A, so we minimize the effects of fringing fields. Here we only need to assume that the conductor plates have an infinite extent in the y direction so that our electric and magnetic fields will not vary with y. All right. Once again, this is Maxwell's equations for a time harmonic wave. So we have a single frequency wave, frequency omega. Then the curl of H can be expressed as j omega epsilon E, because basically when we take, if E varies sinusoidally as cosine of omega t, we can write that as e to the j omega t, e the exponent to the j omega t. And then when we take the time derivative, which was what was on the right side of Maxwell's equation, we generate this j omega E. Likewise, we generate a minus j omega mu in the equation for the curl of E. Divergence of E and divergence of H are both 0. We're assuming source-free region, so we have no charge or current distributions. The boundary conditions are going to remain the same, that the tangential E field will have to be 0 and the normal H field will have to be 0 at a conductor boundary. So we can rewrite these equations by combining, as we did in the past, to get Laplace's equation, where this term J beta is actually what we would have represented as gamma, and then in a propagating wave that has a beta or a k, we would substitute that for gamma. Okay, well, so let's go back just one moment. These divergence and curl equations as well as Laplace's equation. These are basically equations in 3 dimensions. So in general, H will have an X, Y, and Z component, as will E. And so we could actually write separate equations for each dimension. And in fact, that's what's represented here. So they can be written in component form. Here we're actually illustrating them excuse me, in rectangular form, but and that's because we're working with a rectangular geometry. But for example, if you had a cylindrical waveguide, then you would be writing these in cylindrical coordinates and so on. So in our case, because we have parallel plates and it's a nice rectangular geometry, then we can express the curl equations as partial derivatives in x, y, and z. So that's what's illustrated here. So these three represent the curl of h equal j omega e epsilon e, where we have the x coordinate, the y component, and the z component. And then these three on the right represent the curl of E equation, where once again we have x, y, and z. So if we assume propagation in the positive z direction, all of the fields then will vary as e to the minus gamma z, where gamma is alpha plus j beta, where alpha and beta are both real. And so in this case, when we talk about waveguides, we'll consider two cases. Remember, we have a lossless dielectric, in which case alpha would be 0, and so we would have a propagating wave, cosine of omega t minus beta z. The other case is when beta is equal to 0, in which case we will have e to the minus alpha z cosine omega t, where gamma is equal to alpha, and this is referred to as an evanescent wave. Now you will notice that our alpha, beta, and gamma have a line over the top. That is because once we are in a waveguide, then gamma depends not only upon the material, but it also depends upon the geometry of the waveguide. And so that's where this concept of modes will come in. An evanescent wave is a wave that doesn't propagate, but it exponentially decays with distance. And in the cases that we'll be discussing, the evanescent waves decay fairly rapidly. So we'll look at more specifics later on. So here is repeated then our curl equations in terms of components x, y, and z respectively. So those two curl equations actually end up becoming 6 equations, one for x, one for y, and one for z, for the curl of h and the curl of e. Now remember that all of the fields, let's go back, all of the fields are going to vary as e to the minus gamma z. So basically then what z derivatives will do will be generate a minus gamma term. And also remember that the fields do not vary in the y direction, so all of the partials with respect to y are going to go to 0. So what this means is, for example, if we look at this first line, let me get a highlighter. If we look at this first line here, so this one, that's a pretty bad circle. But if we look here, you see we've got the partial of, this is in the h direction, this is the curl of E, and so if we take the x component first, it's partial of EZ with respect to y, but remember all the partials with respect to y are going to go to 0 because all the fields are constant in the y direction. And then we have minus the partial of EY with respect to z, but remember all of the fields in the z direction vary as e to the minus gamma z. So when we take the derivative of this, basically we generate the function back times gamma, times the negative sign, which is negated by this negative sign. So this first equation here is going to reduce to this one, and the second equation reduces to the second one here, the third equation, the third, and so on. So out of this, we get a simplified version of our x, y, and z component equations. And so each one of these then is going to provide some relationships.